In the first two videos, we looked at sort of both ends of the scale. In other words, lightweight residential construction, which a lot of it is going on today, where they're building buildings probably better from an engineering standpoint, but they're building them so much better that they can use less material, so they burn up quicker. I mean, it's just that simple too. They fall down quicker than the old 20-minute rule that most of us were raised with. If you looked at just the times in that kind of in that first video, we shaved 3 or 4 minutes off that 20-minute rule. In the second video, we looked at a classic fire in a building that we've been doing for the last 200 years almost in the fire service. Heavyweight commercial building, large floor areas, big-time roof systems. They're not sprinklered. Certainly in our community there's not. There's 150 square miles of unsprinkled commercial buildings that if we build them today, of course, they'd have to be sprinklered. They're mostly heavily fire-loaded. Some of them are mixed occupancies. If you go up and down those commercial streets, every building contains a different kind of a content or process or a use, so it actually adds to the hazard to them. And we tried to sort of look in a little bit more scientific way, by virtue of having NIST help us provide that information, just how those buildings behaved and reacted, and sort of what are the time frames. How do we create tactics, strategies, incident management systems? In other words, how do we develop an operational approach that simply does the best job picking up the pieces on the bad day that structure has with the people inside it? And how do we protect our firefighters? In other words, a huge adventure for all of us today is looking at the safety and survival of our firefighters. And I think that necessarily us using that kind of information is going to help both those things, helping the customer who is unprotected and the firefighters who come to it with a pretty sophisticated safety system, but a system that nevertheless has some limitations to it. And when we outperform those limitations, what we've got to do simply is get away from that hazard. There isn't anything else we can do. When that building collapses on us, when it flashes over, when we become unprotected in the superheated and toxic products of combustion, we become just like Mrs. Smith in that process. And that certainly is not acceptable to any of us today, particularly. There's a lot of discussion in the fire service about lightweight construction and heavyweight and conventional construction. And we used to nail buildings together with 10-penny nails with 2x12s, and now what they're doing are gusset plates and all that, and obviously that's an important part of us looking at buildings. But there's two things that occur to me about buildings. First, they didn't build them to have a fire in them. The buildings that we're going to today were not built to have a fire in it. And the people who built those buildings, and I think we're going to hear that from the guys we're going to hear from in just a second, are going to tell us that really buildings are not designed for firefighters to run into. They're designed to get the people who work and occupy them and live in them out of them if there's a fire. That's an interesting perspective for us to understand. The other thing is when they burn, any of them and all of them, if they burn long enough, they're going to fall down. It's an unnatural act to take a bunch of building material and stick it up in the air, hook it together with a bunch of connectors, set a fire in it, and have the connectors get destroyed by that fire. It isn't real complicated when we really look at it. Now, what we need as the fire service is new, better information about what are the dynamics of those buildings when they're on fire. And the more we listen to the people who design them and build them and somehow manage the construction and the occupancy of them, the smarter we're going to be when we have to go in there when there's a fire in one of those structures.
Well, as a structural engineer, we normally don't consider fire issues. Those issues are normally considered by an architect. Although as an engineer, we're certainly aware that the assemblies that we design need to meet certain fire-rated requirements, and we work with the architect. We're aware that wall A is a 1-hour wall, wall B is a 2-hour wall, and we're aware of the type of occupancy that a building may have. But normally we don't worry about those issues. Those issues are addressed by an architect.
Is that the stated purpose of, say, the Uniform Building Code is to provide a minimum standard to safeguard life, health, property, and the public welfare by regulating the materials and the quality of the construction. nowhere in there does it say we're going to make sure that we can protect this building from an incident occurring inside the building. The whole idea by protecting public welfare, of course, is that if a building is on fire, has an incident, we're protecting the adjacent structures, the adjacent public ways where people are exposed to it who have nothing to do with that building. Start with things like fire sprinklers, automatic fire sprinklers. Buildings are often compartmentalized, using fire-rated walls to separate them. We look at protecting the occupants through the means of egress. They might be protected corridors or fire-rated stairwells, occupancy separation walls that protect the occupants of one portion of a building from the hazards in another portion of the building. Again, driven toward giving them time to get out of the building. Means of egress are a big part of the code and in fact are a big determinant in the planning and design of almost any building. But I think it's interesting to note that those means of egress have become, over time, particularly I'm thinking of stairwells here as an example, have become also the means of ingress to fight the fires, but they're not really designed for that. We design for the passive use, the need to get people out of the building, and then we kind of don't care about what happens after that. Once the occupants are safe, if the contents of the building can be protected, that's great, but saving the lives of those people is first and foremost. Good design doesn't always recognize firefighting operations. Always recognizes getting people out of the building, but not always getting people back into the building to fight a fire and protect either people or the contents.
So basically, a building has a safety factor, and part of the theory of engineering is that safety factor accounts for things that we haven't thought of and haven't considered. One of those things that we don't normally consider in a building is fire. We know that fire is going to happen to a building. We know it's going to weaken structural members, and we know that from a life safety standpoint, we want our building to hold up during a fire so that people can get out of the building and so that the building won't collapse before people can get out. And so part of the safety factor, even though we don't directly attribute it to fire, does compensate for fire. So we certainly do not design buildings so that this building will collapse at the moment it gets past the design level. We want to have a cushion for that particular situation. And we have complex buildings where a fire may start in one area and there's supposed to be a draft stop or a fire stop that will keep it in a column, for example, a frame column, and it's not there. And so a fire can start in one area and spread to another area. We have framing conditions that may not be put together adequately and maybe in a collapse condition just because of their complexity and the failure of the workers to understand the intent of the designer. If the designer was able to fully express his intent, that may be on the verge of failure even before the firefighter gets there. So we have a system today, to a large extent, where we have a labor force that's not as skilled and as trained as it was in the past, and we have buildings that are more complex. We have building departments that while they have a mandate to offer as much protection to the public as possible, cannot possibly enforce all of the requirements of the building code, and this is kind of what we're dealt with. So when firefighters go out to our modern framed buildings, they have issues to deal with that are a whole lot different than they were 50 years ago.
One of the challenges we have when we start looking at managing our operations is trying to package it up so people can understand it. And the first thing, I think, is just simply our tactical priorities. As we say that the approach that we're going to take when we go out and extend structural firefighting operations is going to be the first thing is rescue, then fire control, then property conservation, then customer stabilization. Now, as that lines up the tactical approach that we're going to take to conducting that structural firefighting operation. The other thing is that as we go through those tactical priorities, we need to have some notion of how we're going to manage risk. Now, I think what a lot of the fire services has started to adopt is a real simple, straightforward, three-level risk management plan. The first one is to say, where there's a savable life, we will take a big risk. And I think that that's the highest and finest tradition of the fire service, and most of us don't even question that. I think the second one is that we say, we have, and we still do, is that we will take we call it a small risk in a highly calculated manner to protect savable property. And let me give you an example of that. is that we go to Mrs. Smith's kitchen fire, and what we do are those tactical priorities, and we do a primary search. We verify that everybody is out of the structure. I think that most of our fire departments will continue to press an interior attack, even though there's some risk to our firefighters, based on our safety system, and we will continue, and I think most of us manage that in a very routine kind of way to complete that extinguishment. In other words, moderate risk in a highly calculated manner to protect savable property. The third level, though, is to say we will not risk at all for property or lives that are already lost. Now, obviously, it takes a great deal of experience and judgment and system support and team management to be able to do those under fire conditions and to pull that off successfully. In other words, it's easy to sit here and just rattle it off. But at 3 o'clock in the morning, when you've got to make sense out of a lot of different things that are happening at once, that's a pretty elegant kind of challenge for fire officers to be able to make sense out of that and to actually stay in sort of those boundaries in the process. But I think that that's a pretty good beginning point for us to make some sense about how we're going to approach those operations. We wanted to get a little bit more scientific information to support the risk management plan. So what you're going to see next is two very experienced doctors who looked at the warehouse burn and looked at the profiles as far as CO is concerned. Now these guys are experienced, very capable, again, downtown doctors, let me call them that. They're very practical guys. They run a trauma center and a burn unit. Now they're not firefighters, so they take a pretty scientific approach to it. But I think that this is extremely useful for us to begin to bring more information from different people. In other words, here in this case, these are the guys that we're going to take customers to who have been processed through this risk management plan. In other words, they know the most about the continuing effect of what we tested in both of those burns.
I think the assessment on the video itself, that within 5 to 7 minutes, if you as the fireman haven't responded and actually in the building, I think everybody inside the building is going to be lost. So I think it really gives a time frame, especially for the firefighters, to determine whether or not it's even safe or feasible to even go into the building.
Well, one of the necessary factors for a fire or for combustion to occur is oxygen, and in a closed space, that oxygen is going to be used up very quickly. And we saw that on the first test burn, that the fire sort of burned itself out and then started back up again when it was supplied oxygen. And this can be a real problem for people who are trapped in that burning building, because the levels of oxygen that they are breathing drop to precipitously low levels, and those patients rapidly become confused and unconscious just from lack of oxygen. In addition, you have buildup of high levels of carbon monoxide, which only makes the problem worse. So it's really sort of a double shot at one time. The hemoglobin in our blood preferentially binds to carbon monoxide. Nobody really knows why that is, but it is. And given the choice between binding to oxygen or carbon monoxide, it will bind carbon monoxide. And so just even relatively low levels over a long period of time can cause very severe carbon monoxide poisoning. And obviously, if you're exposed to high levels for a brief period of time, that can cause problems too. Generally, at about the 10 to 15 to 20% level, you begin to become confused. And that can be a real problem for people in a fire and for firefighters, because they become confused and the decision-making capability goes away. So even though you're awake and conscious and moving, you're not thinking clearly and you're not making good decisions. Somewhere around the 30% range, people become unconscious, and somewhere around the 50% range, people die from carbon monoxide poisoning. Well, we think that people who are found unconscious in an enclosed space fire generally do very, very poorly, and if they survive, it's distinctly unusual.
Over 200 degrees, not very well. For that matter, as we were just discussing earlier, probably, once you get over 120, 130 degrees, it's only going to last a few minutes. So when you're looking at a building here that got to a maximum, I think it was 1,480 degrees, it would be literally seconds before you would be killed just from that alone. So definitely a lethal combination. As I said before, I think I agree with the 6 to 7 minute mark, which without a doubt was no one was going to survive. And I think you saw it within four minutes in the one building, 6 in the other, that the CO levels were high enough. That was the first thing. The second thing I found interesting was, I think it was within 4 minutes, smoke was actually coming outside. It raised to the ceiling and then dropped down and was coming out the doors or the windows. So literally within 4 or 5 minutes, you're engulfed in smoke that you can't see through. The same thing with the television camera. Within 4 minutes, you couldn't see probably your hand in front of your face. So if you're trapped in the middle there, you're a goner. So I think it's a whole combination, but I think maybe that might be the point for you and the fire departments will be, if people have been trapped in there a 5 to 7 minute period, it's probably not worth going in there after them. And but like I said, I think that's not a long time, considering that it's going to take you a couple minutes, even in the best circumstances, to get to the fire. So it only leaves about 2 minutes for you to go in, extract, come out. That's kind of hard to swallow when you're Joe Public thinking, well, I'm a goner. And I think that also probably leads into your whole ideas of pre-fire prevention, smoke detectors, safety plans, all those things people really take for granted and don't think about.
Well, I think that there is a general misconception as far as what happens within a fire, and I don't think that in general people realize the temperatures involved and the toxicity of the smoke and the devastating effect of lack of oxygen. And you put those three things together, and just in a short period of time, you are going to be dead, and there's no way that you're going to be able to be rescued.
When you listen to those two doctors, you kind of get a flavor of what they do every day. And I thought they were very interesting characters and very informative. I think we need to put it in perspective. These guys are clinicians. And the people that we bring them, in other words, the customers that we bring them, if you sort of think of a trauma center and a burn unit, particularly when you're talking about fire customers, in other words, people who have lived through being unprotected in the products of combustion, these two characters are not too optimistic, and I think that you sort of got that flavor as you were listening to them. I certainly did in the process. I need to reemphasize, these guys these doctors, these physicians look at their customers in very clinical terms. We have to look at those customers in very tactical terms. We don't mean by this video to make everybody a trauma surgeon. In other words, we're firefighters, and we've got to take tactical conditions and make sense out of them, because nobody knows what we can do and what we can't do outside of our service any better than we do. But I think, again, it's realistic, and I think enormously useful for us to listen to the kinds of things that they say, because they're involved in the food chain of us somehow protecting and then treating these people who have lived through a fire experience. We've listened to an engineer and an architect who sort of give the birth, they're in the birthing process of these buildings. We're going to listen to and look at a fire protection engineer. That fire protection engineer's discipline really has to do with what occurs to that building when it's burning. In other words, he's sort of the trauma surgeon for that building, as opposed to the docs who are the trauma surgeon for the customers. He looks at how that building is built, how it's managed, how it's occupied under fire conditions, and how do you protect that building, how do you manage that risk. He obviously knows a lot about the firefighting process inside that building, because he sort of looks at the beginning and the middle of that, of the history of that building, and what happens to it simply on the day that it's going to host a fire. So we sort of need to listen to his perspective, because it's very special when he talks about the characteristics that that building has when it's burning in the process.
There's limitations on any structural member, whether it be a glulam or it's a structural carbon steel I-beam, or it's an OSB beam. And all structural components have limitations, and those limitations are measured and well understood, and robust safety factors are built in so that those design limits are never exceeded. What happens is that the building works great until it's on fire. Then what happens when it's ignited is that you now have structural components that just fail faster because of the fact that they're built using weaker methods. There's no mechanical fasteners. It is not one solid mass of cellulose like a 2x4 or a 4x8. What it is, it's a lot of little pieces of wood that are glued and compressed together. And whenever that happens it's kind of like a truss. And you take one part out of any truss and you get structural collapse. What happens here is that once you thin that wood enough, I term it delamination. Once you take off enough of the layer of that thickness, you get the same failure. I never want to be one that says that everything can be predicted, but you can estimate pretty close. We saw from the NIST burns just on the commercial structure that the CO levels exceeded the limits that were thought to be calculated. The fire scientist at NIST said our models for calculating CO are invalid based upon some of the things that we've seen, and that showed up in the NIST report. What it tells me is that once you get into these really high elevated CO levels, it's over with from a life safety standpoint. I don't think it's a firefighter's responsibility to go in and make a rescue whenever the conditions already indicate to us that the occupant's survival is nil. The CO level has reached such a high level that there is no chance of resuscitation. I'm not a doctor, but I'm sure if we asked one, they'll probably conclude that. The other thing that we forget about is carbon monoxide is it's a flammable gas. So when you've got these high elevated CO levels inside the building, and once we reach that range to where combustion is underway, that gas is burning in there. It's consuming even more of that wood structure. So it's not just fire impingement, it's not just the radiant energy, it's our actual fire gases that are contributing to these rapid failure rates. What we saw in the NIST scenario was what's going to govern when collapse is going to occur is going to be based a lot on your fuel load that you have inside of the building. The NIST burns were used pallets. Let's face it, pallets are very robust, fast-burning, high heat output kind of material. But what you saw from the NIST file is that if it ends up involving these high challenge commodities like flammable liquids or solid plastics or those type of things, collapse may happen even faster in those type of cases. Again, you're going to have to go back to your fire ground indicators and do your risk management when you're looking at this thing. What you have to remember is that for every minute that it's burning, the degree of damage to that structure is increasing accordingly. And we never think about collapse from that standpoint. We think of collapse as the failure. What the failure is that you had a fire and you weren't able to get there early enough to get water on it effectively. The problem is that it's not predictable when collapse is going to occur, but we know from these tests at least that the 20-minute rule ain't going to give it to you. Because if you follow the 20-minute rule on the fire ground, well, it's going to be on the ground in less than 20 minutes. And that's the difficulty for the fire service, because we want a nice, quick, clean, simple, easy rule. One could say that probably 5 to 7 minutes is the best opportunity that you've got in there. What it should tell you is that at 5 minutes, if conditions are not going your way, really think about what's happening in the 6th to 7th minute. Because after that period of time, if you haven't got it knocked down, if you're not getting control, if it's in the attic and you're not getting this structure opened up and you're not getting water on that fire, collapse is going to happen soon. And we can't predict when it's going to occur, but we know that your window of opportunity for getting out and getting your crew out and assembling your crew and being accountable for your personnel is rapidly diminishing.
Standard ways that we make sense out of the tactical priorities in the risk management plan. In other words, the way that we integrate those is by developing the overall incident strategy. And those strategies, we've kind of simplified strategy into offensive and defensive. Offensive is aggressive interior operations that attempt to cut the fire off on the inside of the building. Defensive strategy is exterior attack to limit the loss into that fire area and protect the exposures. One of the ways the incident commander manages and packages up those operations in a standard kind of way is by always asking themselves, can we continue to operate inside? And I think that a lot of the information that we have in these 3 videos really is sort of the basis for a lot of what it takes to make those decisions in a very practical, street-oriented kind of way. Now, one of the things that IC has got to somehow evaluate, along with information that he or she is getting from all over that incident site, is what are the conditions on the inside of the building, the top of the building, and the 4 sides of that building, and the basement of that building, if you have. Now, the 7 sides of that building. What they have to do is add that up, process that, and make a decision simply about can we stay inside or do we have to abandon that interior attack. Obviously, when you listen to those physicians talk about the survivability profile, that exists in a pretty narrow window. When you listen to those architects and the engineer, they describe how that building was put together and how that building comes apart. Those really become the dynamics for that IC to somehow process, integrate, connect together, and then translate it into a very practical, street-oriented kind of decision about whether you can stay inside or you got to get outside. Now, it isn't real complicated, but it is absolutely critical that we do that. Now, we're always going to conduct standard operations. In other words, the issue is, where are we going to do that? In other words, what's the location of that, inside, outside, and what are the dynamics and the information that we have to somehow keep that strategy current, simply to match the current conditions that IC is faced with in the process. Pretty practical kind of a challenge, but obviously a critical one for the survivability of not only the customers who are inside that fire area, but our firefighters who are going in to do offensive operations. So we need to somehow sort of synthesize all of this information that we're packaging up to somehow be able to make better sense out of that when we're out there actually doing it in the process. What I hope we can do with this is to get some better information that at 3 o'clock in the morning, when you're out there looking at that thing burning, that it cues something in us to say, I remember what that person said. Let me say what that expert said about this. I think the tests were a chance for us to stand back in a way that we normally don't get to do, and to look at sort of the science of that building burning down. Nothing remarkable about them. We've watched those buildings burn for the last 200 years. But I think when you got a bunch of scientists who hook them up with equipment to measure what's going on, we're going to get at least a little bit different perspective on time, temperature, the nature, the dynamics. In other words, that whole picture is maybe in a little bit better focus. This isn't the end all for us. In fact, we hope that this is the beginning, perhaps, of us taking at least a little bit more scientific approach to having information to add to what we do out in the street every day. The people who we listen to are not firefighters. We are called upon to go out as fire officers and make decisions in front of burning buildings. We are, and I think we really are, the experts in being able to do that. I think that this information contributes to us being able to do that better, and perhaps it adds a little bit different level of realism to what we do. In other words, we listen to the people who design buildings, describe sort of how those buildings come apart. We listen to doctors describe how profound the products of combustion are on the human body, very simply. We listen to a guy who's a very skilled fire protection engineer, who's been around for a long time, so he has a lot of experience, describe what happens in sort of the limited window that we have just for fire control, that past a certain point, we cannot put enough offensive water on that fire to put it out in the process. And so I think that information is something that we need to take back and crank into the regular approach that we take to firefighting operations, to tactics, to strategy, to incident command, in other words, to the way that we conduct operations, just simply to do it more effective, to do it smarter, and to do it safer. I think that is a righteous thing for us to do, and we hope that all of this, these 3 videos help in that process. And we thank you very much for looking in on them.